All right, we will now move on to the current transformer test. What are the tests we perform on a current transformer? Of course, from the diagram we saw, the first thing I want to verify is the ratio. I want to see what the ratio of the current transformer is like, meaning right now I have do I currently have, if I put 1000 amperes on the primary of the CT, will it convert to 1 ampere on the secondary? If it doesn't convert to 1 ampere, what will the ratio be? Do I have a limit for the ratio? Of course, not me, or take 5B20 and take 0.255. And we agree that 5B20 means 5%, or your conversion ratio should not exceed 5%, up to, if the current is up to the accuracy factor multiplied by the rated current, meaning up to 20 times the rated current. And if you are in the metering core, the ratio error should not exceed plus or minus 0.2%, or 2 out of 10% up to 5 times the current. Here, I want to make sure of this. I will inject a current, for example. But ultimately, I want to ensure that the secondary current for me comes with a value that does not exceed, or the error in it does not exceed, my class of the current transformer. Secondly, the polarity. I want to make sure that I have set the correct polarity, because this will depend on connecting it later to the metering device or even to the protection device. When I explained to you, I explained it simply and told you that if a meter device reads the exported power as imported, while it is the power source, but it reads it as imported, then the direction of the power here becomes different. So now, are you giving or taking power, especially if you are talking between countries and between stations and so on? How will the accounting be added? Of course, in protection, it's the same thing. The protection zones are divided into forward zones and reverse zones. I'm talking about distance. I'm speaking generally. Even the direction over current direction errors fold. You have a forward zone that trips with a time delay, and reverse zones that trip as a backup protection with a different time delay. Therefore, it is not acceptable for the fault to be in the forward zone, meaning on my line, and I see it as being in the reverse zone, and start applying a large time delay or no time delay at all, or not tripping at all if I haven't set my master protection to trip in the reverse zone. That's correct. And it is also not acceptable for the fault to be in the reverse zone and see it as if it were forward and start tripping my breaker and so on. So here, what is the priority? Among the very important things is also the secondary winding resistance. I want to ensure that the resistance of my windings is intact to make sure that there are no cracks or issues in my windings. If there is a crack, fracture, voids, or anything that could lead to an increase in the resistance of the secondary windings of the current transformer, I want to ensure the magnetization curve. What is the knee point voltage at which it saturates, or just before it fully saturates? What is the excitation current at that point? And does the current actually increase by 50% when the voltage increases by 10% or not? I want to see the behavior of my curve completely. And I want to measure the burden, the load with precision, because I told you that I have a rated burden that cannot be exceeded. So what's the problem if you exceed it? No, there's a very significant problem. What's the problem? Let me show you what the problem is. This problem will arise from the equation I mentioned to you. The equation I told you about, I said that the knee point is like this, the knee point I mentioned to you. It is a factor, and this factor could be the accuracy limit factor if I am talking about a protection core, or it could be the security factor if I'm talking about, what am I talking about? I'm talking about a metering core. Someone might say to you, why do you say security factor and write it as FS, Squad? Because it is actually an abbreviation of a French word that means security factor in English. All right, fine. Multiplied by the secondary current, multiplied by the resistance of the CT winding, which is RS plus the burden resistance, right? Great. I told you that in a protection core, this core is designed so that my CT reaches the saturation point, meaning the current reaches the knee point at a number of times greater than the accuracy factor multiplied by the secondary. When does this happen? If the burden connected is the rated burden, right? The rated burden, correct, or am I wrong? You said it's correct. Okay, let me tell you something very simple now. The knee point is related to the iron core, and this iron core hasn't changed. You have it made of silicon, steel, or whatever, and this iron core is constant for you, right? Or am I wrong? So the saturation point for the iron core depends on the dipoles, which is a constant, right? And the secondary current is 1 ampere, which is a constant. The RCT, you get it with a certain number of turns, which is a constant. So what is variable for you? The kilovolt ampere, a factor with the burden. So of course, both are multiplied on the same side of the equation. This means that the kilovolt ampere factor is inversely proportional to what? It is inversely proportional to the burden. This means that as the burden increases, this factor decreases, and as the burden decreases, this factor increases. So of course, if I am working in a system, the protection core, if I am working with a protection core system, what matters to me? If I increase this burden beyond the rated burden, I might find that I reach saturation at fewer multiples of the accuracy factor. Consequently, I will have a problem. That's why I need to ensure that I reach the rated burden or less than the rated burden. So I maintain high saturation at a high number of multiples of the current, which is very good. However, if I come to the metering core and increase beyond the rated burden, my factor will decrease. You might say that's excellent because I want the factor to decrease, but it will tell you no. Why? Because if you increase it beyond the limit, you might find that your factor becomes 1 or saturation occurs. At one time, the rated current, 1.5 times the specified rated current should not cause saturation. If you significantly reduce the burden, the factor will increase, which means it will increase. If it increases, what will happen is that you'll find there's a problem allowing high currents to pass to the meter device and through your winding, causing an issue. That's why you must always maintain a balance with the burden.